All right, so question 1 here, and I believe this is a this was a calculator question because we have decimals here, calculator question. So a tank has a height of 10 feet. The area of the horizontal cross section of the tank at height h feet is given by the function a. Look, here's a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values of a of h are given in the table above. So it looks like we have 4 values. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume in the tank, indicate units of measure. All right, well, it's telling us to use a left Riemann sum. That apparently will approximate volume in the tank. So we'd say volume is approximately equal to, and I guess it would just be the integral from 0 to 10 of a of h dh is what they're saying right here. All right, so this integral, actually, I guess we should probably say equal to here. This integral is approximately. So this is where we would need the approximately, or you can just go straight from volume to is approximately equal to. And then we'd use the Riemann sum here, and we want to use the left side. So here's one interval, here's the next interval, here's the third interval. So this is the left side for the first one. So it's 50.3 times the length of this interval, 2 minus 0. The next height is going to be 14.4 times the length of this interval, which is 5 minus 2. The next height is going to be 6.5 times the length of this interval, 10 minus 5. All right, and honestly, that's enough right there, but we do need units of measure. So these are square feet, and this dH would give us another feet. In other words, we have area here, we're integrating, we're getting volume, so we should know that volume is cubic units. So this should be feet cubed. All right, now you can leave it like this, or you can try and work it out. Either one's fine. Like, honestly, again, if you get it to the point where it's just something that you can type into a scientific calculator, that's a good enough answer on the AP exam. So we could leave it like this. That would be fine. If we want to actually work out this and get a number, I'm too lazy to get my calculator out. It looks like it is 176.3, right? Those are the values we had. Yep. So this, hopefully you got 176.3, and again, cubic feet. Part B. Does the approximation in A overestimate or underestimate the volume in the tank? Explain your reasoning. You might actually. So like if there isn't an approximately equal to somewhere, you might lose a point. Right? Because that's not technically true, but that is an excellent question. So make sure if it says that you're estimating, like if it tells you to approximate something, then you probably should have the, almost equal to or approximately equal to sign somewhere out there instead of the exactly equal to sign the whole time. All right, so just something to keep an eye on. All right, so is it an overestimate or an underestimate? Well, what do we know about the function? Well, we know it's continuous and we know it's decreasing. So like it will look probably something, there's a decreasing function. Doesn't really matter. Right? So, and we're doing left-hand rectangles. So what do you think? Looks like we're getting some extra area here and some extra area here and some extra area here. So this is going to be an overestimate. Since we are using left-hand rectangles and the function is decreasing. You might be able to just get away with saying overestimate and then draw the picture and like say, look, there's extra area here. That might be enough. Let's see what they said. So let's see. There's an overestimate because the left-hand Riemann sum is used and A is all they said was it was decreasing. So honestly, the picture probably would be enough. So yeah, for the first one here, we got 1 point for the Riemann sum and 1 point for the approximation. Yeah, that's a true good question. You probably can't draw on the exam this year. So yeah, if we wrote what we wrote with the units, like that with the units, that would be full credit. Here we just said it was an overestimate and we gave some sort of reason. The graph would be enough for a reason, I think. But if you said just because the function's decreasing, that was also enough. All right, so continuing on, part C. The area in square feet of the horizontal cross section at height h feet is modeled by the function f given by that. So instead of using this, now we have f gives us the area at any certain point instead of these particular points. Based on this model, find the volume of the tank, indicate units of measure. So for C, now we've got the function. So now the volume should be equal to the integral from 0 to 10 of just this function. Right? And the units of measure were going to be still cubic feet. All right, so we do probably want to type this into our calculator. So like this is a calculus exam. They do want to check to see if you know how to do calculus. Looks like I'm not going to move my calculator. There we go. Sometimes it just doesn't want to listen to me. So remember math, then number 9 is how do we get to the integral sign. So if we're going from 0 to 10, I don't know what mode I'm in, so hopefully this will work out. We've got 50.3 divided by parentheses, second e to the 0.2. Our variable here is x, so we used h, whatever, it doesn't make a difference. Out of the exponent plus our variable, close the parentheses from the bottom, and then dx. And we get, so it looks like we got 101.325 cubic feet. That's a good bit less than it was before, but you know, we said it was going to be an overestimate, and there it is. So we get 1.4 setting up the integral, 1.4 the answer. And I believe probably with units because the problem did specifically say units. So yeah, you got 1 point overall if you included units in all the parts that asked for units. It was in the end. All right, part D. Water is pumped into the tank. Okay, so now we're filling it with water. When the height of the water is 5 feet, so when h equals 5 feet, the height is increasing at the rate of 0.26 foot per minute. So that's a dH dt, the rate of change in height with respect to time, 0.26 feet per minute. Okay, this makes me think it's probably some sort of related rates. Using the model from part C, all right, so that was this thing that we did from part C, find the rate at which the volume of water is changing, that's dV dt, the rate at which the volume is changing with respect to time, so dV dt, when the height is 5, indicate units of measure. Well, we can say units of measure right now if we wanted to. So everything was in feet, the volume is changing, so that's going to be cubic feet, and our time that was given is per minute. So that's going to be our units right there. All right, but if we want to find dV dt, well, here's the function for V. So we could say, I suppose I should put a D here, V equals the integral from 0 to some time, say, t. I don't know if maybe I don't want to use t. Well, no, I could probably still use t. That'll probably work. No, because we're going to a height. We don't want to do that yet. So we're going to a height of our function here, f of h, but I don't want to use h again because I just use h as my bound. So I'm just going to say f of x dx. So I'm just using a dummy variable. I'm basically saying this is f of x instead of f of h because I don't want to use h. All right, so that means if I take the derivative of this, dv dt would be the derivative with respect to time of the integral from 0 to h of f of x dx. All right, so now I'm differentiating the integral. So I could take the integral and then take the derivative of it back again. All right, well, what that would get me then is basically a chain rule. So it would get me f of h times dH dt. All right, now if you don't believe me, follow me here. We get some capital F of x. Say when we integrated, we're going from 0 to h. We'd plug in h, f of h, minus we plug in 0. Then we take the derivative. Well, if we take the derivative of this guy, derivative of capital F would bring us back down to lowercase f, times the derivative of the inside, which is a dH dt. If we took the derivative of this, we'd get 0. So we do just get that guy right there. So f of h times dh dt. Well, f of h is this function right here. And dh dt is that value right there. So we just got to plug in. So we just need to do 50.3 over, and remember h is 5, over e to the 0.2 times 5 plus 5, work that out, and then times 0.26. So it's just a matter of plugging that in the calculator. And let's see, what do we get if we plug that in the calculator? We get, see, f of 5 times that, 1.694. And we might as well put the units down here. This is cubic feet per minute. The rate of change in the volume. All right, now does it ask us to explain anything? Why don't we have to take the derivative of the whole equation like in other problems? We actually, well, because we're taking the integral to get the volume. That's why. So like if this was the volume function, then yeah, we'd have to take the derivative of it. But this isn't the volume. This is the area of a cross section. All right, so this is what we have to integrate to get to the volume. All right, so we basically said that right here, volume from 0 to whatever height we've got is just the integral of that function. It's not that function by itself. All right, so then when we take the derivative of the integral, that's when we get back to the original function, and we also get a dh dt from the chain rule. Yeah, tricky. I bet a lot of you probably just took the derivative of that function and then put a dh dt, and yeah. Yep. It won't do it for you. You could still get the unit point though if you got the units right. All right. Did it ask us to explain it? No, it just said indicate and find it. Okay. So we don't have to write a sentence unless it says to explain. All right. So let's see. We got 2 points for getting dv/dt. So 2 points. They just did it chain rule style, but again, they wrote it out like that, just like kind of like we did, exactly like we did actually. And then they took the derivative, and that got them to that. And then they were like, oh, we got to plug in 5. So that's their notation for saying plug in 5, and then plug in the 0.26 for dh dt. And then there's their answer. And they have units right here, cubic feet per minute. All right, the next problem. They love these problems on the AP exam. Love to give you a graph of either a function or a derivative or a second derivative or whatever derivative, and then ask about anything about it at all. So the function f is differentiable, okay, on the closed interval from -6 to 5, and satisfies that f of -2 is 7. So we have one value of f, and this is f prime up here. The graph of f prime, the derivative, consists of a semicircle. Here's our semicircle, and 3 line segments. So line, 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 as shown in the figure above. Find the values of f of -6 and f of 5. All right, so to get to another value of f, we basically have to start at the value of f we've got. All right, so what we could do is to get to f of -6 is we could integrate between the two here. So we have to integrate the derivative to get to the actual back to the function. So what we could say is the integral from -6 to -2 of f prime, the graph we've got up here of x dx, would be equal to f of the, like, so if we take the derivative or the integral of the derivative, it brings us back to f. So it'd be f of -2 minus f of -6. And here's the trick. We're trying to find f of -6. So we can move this over and then we can multiply by the -1. And what we end up getting is that f of -2 plus the integral, actually we're multiplying by -1, minus the integral from -6 to 2 of f prime of x dx will be equal to f of -6. So I just subtracted this over and then multiplied by everybody by -1 to change all the signs. All right, so we just get that. And this was a -2. Yep, sorry. I caught it. You caught it too. I'm glad you're quick there. All right, so now to integrate from -6 to -2, so -6 is right here, -2 is right there. That's just the area of this little triangle here. So this is 1, 2, 3, 4 by 2. So this is 1/2 2 times 4, which is 4. So this thing is just 4. F of -2, they said was 7. 3, ends up being f of negative 6. Neat trick, huh? Next one, we want to do f of 5. So to get f of 5, we basically do the same thing. So we could integrate from, let's go a little higher here. Integral from, so we'd start, negative 2 comes first. So we'd go from negative 2 to 5 of f prime. That would be equal to f of 5 minus f of negative 2. So to solve for f of 5, we just add over the f of negative 2. So we get f of 5 equals f of negative 2 plus the integral from negative 2 to 5. And it looks like we got one more person here. Add their name to the attendance. Gotcha. All right, so now we're integrating from negative 2 to 5. So now we're going from here, so that's 2, that's 5 all the way to there. So we've got this circle, this semicircle here with radius of 2. So this area is going to be, and it's negative since it's below the axis, but it's 1/2 pi times the radius squared. So it's going to be negative, so 4 times 1/2 is going to be negative 2 pi. This guy, we got another triangle happening here. It's 3 by 2. So its area is going to be 1/2 3 times 2, which is 3. All right, so we're going to get f of 5 equals f of negative 2 was 7. All right, then we're going to have this negative area, negative 2 pi, and then this positive area, plus 3. So we get that f of 5 equals, let's see, that's 7 plus 3 is 10. So we get 10 minus 2 pi. And there's our answer. Hopefully that's right. Should we check? Yeah, so one of them was 3. The other one was 10 minus 2 pi. Is that what we got? That's what we got. All right, 3 and 10 minus 2 pi. Cool. Part B. On what intervals is f increasing? Justify your answer. So for part B, f is increasing whenever f prime is greater than 0. This is the graph of f prime up here. So we're just looking for when f prime is greater than 0. So f prime of x is greater than 0 for, let's see, from here to here. So from negative 6 to negative 2. And let's see, it's negative here, but then it's positive again here. So from 2 to 5. All right, so you could say f is increasing on the intervals from negative 6 to negative 2 and from 2 to 5. All right, and you justified it right here. Right there is your justification. So justify your answer. Here's my justification. It's greater than 0. All right. You could also, so this is just the open intervals. You could also just as justifiably write these as closed intervals, and that is perfectly correct as well. I know it might seem a little strange to include the endpoints, but you can include the endpoints, and that's not wrong. In fact, some textbooks say that that's the preferred way to do it. I say it's a little weird to what happens exactly at -2 and exactly at 2, but you can include them and it's still fine. So if you want to see, yep, there we go. So f is greater than 0. I guess we probably should have included -6 there. Therefore, f is increasing. I think we'd still get all the points because we said it was increasing on those intervals. Yeah, I guess we should include that as there we go. All right, part C. Find the absolute minimum value of f on the closed interval from -6 to 5. Justify your answer. So for absolute minimum, we have to do a candidate test. All right, so whenever they say absolute anything, candidate test. All right, so our candidates, our x values, first of all, they're going to be the two endpoints, -6 and 5. And then the other candidates will be where the derivative is equal to 0. So it's equal to 0 right there. It's equal to 0 right there. Technically there again, but we're already including that. That's 5. So -2 and 2 both also need to be candidates. All right. Now, if you want to say, wait a minute, we want absolute minimum and this positive here, so it would be increasing and then decreasing. This is actually a max, and you want to leave out -2, you actually can. Not a problem. But -2 is the easiest thing to find that we've got because the f value at -2 is given. So we want to find the f value of each of these. So at -2, we've got 7. All right, now we actually just found the f value of -6 and the f value of 5. That was exactly what was asked in part A. They're sneaky like that, right? So f prime of f of -6 is 3. And the other one was 10 minus 2 pi. So really the only one we've got to work out is f of 2. So to get f of 2, we're going to do the same thing we did with part A to get f of -6 and -5. So we'd say the integral from -2 to 2 of f prime will be f of 2 minus f of -2. We just add this guy over. So we get f of 2 equals f of -2. I'm just writing it the other way around. The integral from -2 to 2 of f prime of x dx. Now f of -2 is 7. That was given to us. This guy is just the area of this little circle down here, which we found a second ago to be -2 pi. So it'd be plus -2 pi. So in other words, f of 2 is 7 minus 2 pi. All right, so now we want to know which one of these is the minimum, which one's the smallest. So 3, this is roughly 10 minus 6, so this would be somewhere around 4. 7, this is roughly 7 minus 6, so this would be somewhere around 1. So the one that's the minimum is that guy. So there is our absolute minimum. All right, don't say it's approximately equal to 1. Just say that's our absolute minimum right there. Like you can write that, but just to do it in your head. But yeah, think of pi as 3. Easy thing to do. All right, so that's part C. Part D. So for each f double prime of -5 and f double prime of 3, find the value and explain why it does not, or explain why it does not exist. All right, so we want f double prime at -5 first. All right, well, that's going to be equal to f prime at -5. So this is the graph of f prime. So in other words, this would be the slope of f prime at x equals -5. So if we look at -5 is right here. Right, that's a part of this line. The slope of the tangent line here is just the slope of that line. So that would be equal to just the slope of this line. So let's see, this is at 6, 2, and this would be -2, 0. So we could say 2 minus 0 over -6 minus -2. That's plus. So we get 2 over -4, -1/2. Yeah, so it's down 1 over 2, down 1 over 2. Yeah, that works. So that's f double prime at -5. Not so bad. At 3, though, here's 3. We're at a corner. All right, so f double prime of 3 would be f prime at 3. So it's the slope of f prime at x equals 3. Well, for one side, that slope is positive. In fact, we could find that slope. It looks like that slope over 1 up 2, so that slope would be 2. The other side, this slope is negative. It's going down 2 over 2. That slope would be -1. So from the left, like we could write out the whole limit definition and whatnot, but it's a corner. All right. So from the left, f double prime of 3 minus equals 2. And f double prime of 3 from the right equals -1. Since those are not equal, therefore f double prime of 3 does not exist. I don't know if you could just say it's a corner and stop, or if you actually want him to show that it's different from both sides of the corner. Let's see what they say for their answer. All right, so let's see. We got our 2 points for this guy. Absolute minimum occurs when the derivative equals 0 or at the endpoints. So we checked the endpoints, and where the derivative equaled 0. Those are all of what we checked. We got the minimum was 7, so we got that right. And we got 2 points for that. That was it, huh? Usually they have more, but usually you have to calculate this first and that first and maybe even that. So we've already did it earlier. Do we have to use a candidate test? Yeah, I think you did, because you have to check the endpoints and you have to check the maximum. If you wanted to leave out the -2, you could, and you still get full points. Because look, it just says considered x equals 2, answer with justification. Justification means you check the endpoints against this guy. So technically, if you left off this -2, that's not a problem. But if you left off the endpoints or this guy, or didn't check the actual values, or just said this was a max, you still had to check the other endpoint at 5. Yep. And let's see here. So f double prime of 5 is -1/2. That's what we said it was. Cool. That's 1 point. F prime does not exist with explanation. All right. So here's from the left saying it's 2, from the right saying it's -1. So they use the limit definition, one of the forms of the limit definition. And they said that since they are not equal, it does not exist. Right? So we basically did the same thing. We didn't write out quite as much, but we did say from the left it was one thing, from the right it was the other thing. And since they were not equal, it does not exist. So I think that would be full credit for us because we have the answer that it does not exist with an explanation. All right. So that is that. A little bit longer on problems today. Let's take a look at my background. No, let's take a look at the multiple choice here. So it looks like we're doing volumes by washer and disk method. And looks like some of these were calculator questions. Is the volume of the solid R when R is revolved around y equals 4? Well, it looks like it's clearly D. Let's see. So we've got cosine of that and y equals x over 4, and we're revolving around y equals 4. And they didn't give us a graph. So sometimes they will give you a graph. Oh, that's right. I got to turn on that. I'm actually annotating here. So first we need to sketch this just to get an idea what's on top, what's on bottom, where we're rotating around. So we want the region in the first quadrant bounded by the graphs. So cosine of 2 something. So cosine is going to start up here at 2, and it's going to come down pretty quickly. And then it'll, keep going, cosine. It's going to do its cosine kind of thing. Y equals x over 4. Well, it's probably going to look something like that. And this is, I'll put it back here. Y equals 2 cosine of x over 3. All right, so now what we want to do is revolve this around y equals 4, which is up here. So we want to take it and revolve it around that. So that means we're taking this little region here and revolving it around. So in other words, we'll have a little r that goes to this curve, and we'll have a big R that goes to this other curve that's farther away. All right, so little r is the distance between 4 and the cosine. So little r will equal 4 minus 2 cosine of x over 3. Big R is the distance between 4 and this line. So it's going to be 4 minus x over 4. And then the integral then would be, well, it's pi times the integral from here to wherever they cross. Let's just call that, I don't know, b for now. We have to find that. All right, but it's definitely starting at 0. So it's going from 0 to what we're calling b of big R squared. So 4 minus x over 4 squared minus the little r squared, 4 minus 2 cosine of x over 3 squared dx. All right, now we need to find where they cross, which isn't necessarily an easy thing, but you'd probably want to do that on your calculator. And it looks like they did do that on the calculator, and they got that they intersect at 3.397. So you just graph both of them and just say, where do the two graphs cross? So it's I guess I can do that real quick just to remind you how to do that on the calculator. So y equals, goodbye from last week. So we've got x over 4 was one of them, and the other one was 2 cosine of x over 3. And I'm going to turn this plot off because I don't want that to show up. And zoom 6. So there's my x over 4. And here comes my cosine. All right, so they're crossing right here is what we want to find. So second trace, then number 5 for where they intersect. And let's move closer to the point so make sure, they get the right point. It doesn't like it when I continually hit buttons. All right, so enter, enter, enter. And that's where they are getting the 3.3968, 3.397, all right. So let's, more decimal places is fine. And we'd just be throwing that in the calculator. All right, so they're just throwing this all in the calculator and they got 74.255, which is what we have, right? Yeah, okay, that's it. All right. Not super easy, but not super hard either, especially if it's a calculator question. All right, what's next? Just forgot washer method. It's big R minus little r. That's the washer method. Big R squared minus little r squared, I guess I should say. Arc length, we're good. Oh, there's another one. Let's see, let R be the region in the first quadrant bounded by the graph y equals 2 secant and x equals pi over 4, and the x-axis and y-axis. R is the base of a solid whose cross sections perpendicular to the x-axis are semicircles. What is the volume of the solid? All right, well, volume of the solid here is going to be an odd volume. So let's see, we've got 2 secant of x. Secant of x is kind of like parabolas kind of going up, but this would be like y equals 2 secant of x. Pi over 4 would be maybe like here. All right, and we said the x and y axis. So this is our section right here. This is R. And then we want cross sections perpendicular to the x-axis that are semicircles. So let's see, perpendicular to the x-axis. So a cross section would be like this. And then this would be coming out at you like a semicircle with a radius r. And then we'd be taking these semicircles and they would just like, there'd be another one here and there'd be another one over here and there'd be a whole bunch of semicircles coming up at you out of this picture. So what we need is a formula for the area of this semicircle, and that's what we would be integrating. So we would integrate from 0 to pi over 4 along the x-axis, so dx, the area of this little cross section. So the dx would be the width, and the area of this cross section would be pi r squared over 2, since it's just half of a circle. All right, so the pi and the 2 can come out front. The little r is what we need to find. Well, the little r is always just going to be half of that distance. So it's just this guy divided by 2. So it'd be the integral from 0 to pi over 4. We could bring the pi over 2 out front. So this guy can come right outside. Our r is equal to 2 secant of x divided by 2. So the 2's are going to cancel. So our r is just secant squared of x dx. All right, and we can integrate secant squared. Anybody remember what the integral of secant squared is? Isn't it just tangent? It is just tangent. Hey, I can remember things. I'm old, but I still remember a few things. Cool. All right, so we'd get, I think it's back to the right spot there. So this would be pi over 2 times tangent of x from 0 to pi over 4. So tangent 0, so we just need tangent of pi over 4. So it's tangent, so it's pi over 2 times the tangent of pi over 4 minus 0. And now we're just working that out. Tangent of pi over 4 is 1. So we get 1 times pi over 2, and that's where we're getting pi over 2 from. So I guess this one was probably a no calculator question. My internet is unstable. Well, hopefully I won't disappear on you, but it has happened before. All right, here's another one. 8 people missed this one. 2 people got it. Hopefully the questions will load. Let region R be the region in the first quadrant bounded by the square root of x, the y-axis, the line y equals 1, and the region R is the base of a solid. The solid, each cross-section perpendicular to the y-axis, is an isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. What is the volume? This is kind of weird. I don't know if I've ever seen one like this before, but let's go ahead and try and draw this. So we've got y equals the square root of x. We've got y equals 1. And let's see, we've got the y-axis, so that's this guy. So that's this little section right here. This is our region R. And the base of the solid for each cross-section perpendicular to the y-axis. So here's our y-axis. So they're going to go out this way, perpendicular to the y-axis. And they're going to make isosceles right triangles with the right angle on the y-axis. So they're going to come up like this with a right angle here. And there's the isosceles triangle. All right, so that's what we're doing. All right, so that means the area of this little triangle here is what we want to integrate. And the area of that little triangle is this base region times this height region, and then times a little dy. So we need to get the formula for this area in terms of y. So it's this length here, which is the x here. So that means if we solve that, we get y squared equals x. So it would be y squared times the height, which is the same since it's isosceles. So that equals that. So it would be another y squared, and then times a half since it is a triangle. All right. So what we would do then is we'd be integrating from 0 to 1 of this area function. So that'd be 1/2 y to the 4th times dy, because our little widths are going up the y-axis. All right, and we've already got the 1/2 in there. So now we're just got to integrate that. So we can pull the 1/2 out front if we want, but the integral of y to the 4th is y to the 5th over 5. So we get 1/2 y to the 5th over 5 from 0 to 1. Plug in 1. We get 1 times 1 over 2 times 5. So we get 1/10. Plug in 0. We get 0. So we do just get 1/10. There it is. That one definitely was tricky, especially when we had to go in terms of y. So I understand when we have issues when we have to switch variables to the other way. All right, let's see. What other questions do we have that were from this section? So it looks like we got at least 2 more here. So 9 and 13. Disk method. Let R be the region bounded by y equals square root of x minus 1. So that's this guy. Horizontal line y equals 2. So that's this guy up here. The vertical line x equals 1, which is this dark one right here, as shown in the figure above. All right. Which of the following gives the volume of the solid generated when the region R is revolved around the vertical line x equals 1? So we're taking it and we're revolving it around this line right here. All right, so we'll have another side going this way, and it'll look like that. And it'll have some sort of radius here, r. And like we can just do this as a washer, but our washers are going up this something parallel to the y-axis. So this means we would be integrating dy. All right, so the washer method says that this would be pi times the integral from 0 to 2 of r squared dy. Actually, it's not even washer, it's just, they're doing this as a washer? No, they're not doing it as a washer, okay. Yeah, it's a disk method, it's not even a washer. All right, so we need to find a function for this r right here. Well, it's the difference between this curve and this curve. But we need this curve in terms of y, and this one was y equals the square root of x minus 1. So to get this guy in terms of y, we'd have to solve for x. So we'd square both sides, and then we'd add the 1 over. All right, so it'd be this minus this section here, from here all the way to the end here, which is just 1. So our little r would be y squared plus 1 minus that 1, this length from here to here. All right, because from the x-axis or sorry, from the y-axis all the way over would be this, but then we're taking away this 1 every time because that's where we're spinning around. So it would be pi times the integral from 0 to 2 of y squared plus 1 minus 1 squared dy. Now, they probably could have just canceled that out if they wanted to, but they didn't. They left it all right there just to try and make it more confusing, it looks like. The square is outside. It is dy. We're going from 0 to 2, and there's a pi out front. So that's our answer for that guy. All right, one more here, and we'll call it quits. And I'll try to remember to upload the video, but it takes a while to upload these. All right, so let M be the region in the first quadrant bounded by the graph y equals 2x plus 3, the graph of y equals x plus 3. So those are two lines. The vertical line x equals 4. What is the volume of the solid generated by when region M is revolved around the horizontal line y equals 2? Oh boy. All right, well, let's try and graph this and get an idea of what's going on here. So we're really only in the first quadrant. So that's all we got to do is draw the first quadrant here. We've got y equals 2x plus 3. So we'd be up at 3 here. And we'd have a slope of 2. So this is y equals 2x plus 3. And then the other one's, again, starts at 3, but it has a slope of 1. So it's not quite as steep. So this would be y equals x plus 3. And we've got a vertical line at x equals 4. So maybe we'll say this is 4. So somewhere here, vertical line, not very so vertical, but there we go. There's x equals 4. So it looks like this is our little area right here. What's the volume of the solid generated when region M is revolved around the horizontal line y equals 2? So y equals 2 would be here. And that's what we want to revolve around. All right, so if we're revolving that, we're going to have a little radius right here. And we're going to have a big radius right here. So the little r is to this line. So the little r would be x plus 3. And then we'd have to take away from here down to here, this part, so 2. The big R would be up to the top line. So it'd start at the top line, the 2x plus 3. And then again, we'd have to take away this little part down here, which is another 2. So that means our function, our integral would be pi times the integral from 0 to 4 of big R squared. So that's, well, we can actually simplify that. We can say that that is 2x plus 1 squared. The plus 3 minus 2 gives us plus 1. Minus, if we bring in the 2 here, we get x plus 1. And then dx, because we're going along the x-axis, so it is dx. All right, and now we just have to integrate that. We could plug that into a calculator if we wanted to. I don't know if this is a calculator question or if we actually had to integrate it. If we actually have to integrate it, it's not so bad. 4x squared plus 4x plus 1 minus x squared plus 2x plus 1. So we could simplify here. That would be 3x squared. 4x minus 2x is going to give us 2x. 1 minus 1 cancels out. So we're integrating that from 0 to 4. My 4 just looks like a 9 there. So if we integrate that, we get 3x cubed over 3 plus 2x squared over 2 times a pi out front from 0 to 4. The 2's cancel. The 3's cancel. Isn't that nice? If we plug in 4, we're getting 4 cubed is 64. So we get pi times 64 plus 4 squared is 16. Minus plugging in 0, we're going to get 0. So really, it's just 64 plus 16, which is 74, 80. 80 pi. There it is, 80 pi. Yay, I got it right. Woo! And